In this lecture, we shall consider the modeling of RLC circuits. So we will go through first introducing the electrical circuit elements, and then we'll talk about circuit law, and we'll consider examples where we will produce models for systems, the systems being the RLC circuits. So we have considered before in the previous lecture that a system is a set of interconnected elements working together for a common purpose. So in our case, we have circuits as these types of systems. Now the LRC circuits, as the name implies, are circuits that contain resistors, capacitors, and inductors. So the R is for resistance, the L is for inductance, the C is for capacitors. Now, talking about resistors, so resistors are circuit elements that mainly resist the flow of current. The resistor itself physically typically would look like this picture, and then it would have multiple bands on it, which would signify the amount of resistance the resistor has. Remember, we said a resistor resists the flow of current. So mathematically, we can express that the resistance of a resistor, which is measured in ohms, it's equivalent to or it's the resistance multiplied by current is proportional or equal to the voltage supplied to the element. As a second element, in the drawings, the resistor can be sometimes drawn with a little box with an R inside, or a symbol such as this one with a zigzag. Now, if combinations of resistors are used and these resistors are in series, we know that the resulting or equivalent resistance of all of those n resistors in series would be the simple sum of those resistances. If the resistors are connected in parallel, then this relationship holds for the equivalence resistance Req compared to the small resistances R1, R2, and up to Rn that make it up. A capacitor, on the other hand, which has different types of different looks. We have electrolytic capacitors. Some of these are ceramic capacitors, and different types of capacitors, basically, depending on the package that they come with. So a capacitor stores a certain amount of charge Q within an electric field. It is rated by its capacitance C, which is measured in farads. The mathematical behavior of a capacitor is that the current in a capacitor is proportional to the derivative of voltage, or the change in voltage. So I is equal to C dV dt. Alternatively, we can express the charge stored in the capacitor, which is basically the integration of the current, as being equal to C times V. So the charge stored in the capacitor is proportional to the voltage as well. So a capacitor can be expressed by the following symbol, or sometimes a polarized capacitor. If it's an electrolytic capacitor, it can be produced by the following symbol with slightly bent side, like this one. Or if it's a variable capacitor, it could have an arrow through it. Like resistors, an equivalent capacitor for capacitance in parallel would simply be the simple sum of all of the capacitors connected in parallel. If, on the other hand, the capacitors are connected in series, then 1 over the equivalent resistance is equal to the 1 over the sum of all the individual capacitances. An inductor would simply look like it would have a material which is commonly called a core, and a strand of wire wrapped around the core. That should produce an inductor. So it could come in either in this linear shape or in a circular shape, but the construction is it's similar. So an inductor, on the other hand, stores energy within a magnetic field. Remember, we said a capacitor stores energy within stores charge within an electric field. So and the inductor in this case, it stores energy within a magnetic field, and the inductor is rated by what's called inductance L, and the inductance is measured in henries. Now the voltage across the inductor is proportional to the change in current, and that proportionality relationship is related to L, which is the inductance of the inductor. The inductor would simply be symbolized by a symbol like coil, or sometimes like a symbol with a line with pumps. Now the inductor, like a resistor, if the inductances are connected in series, the equivalent inductance will simply be the sum of the two inductances. If on the other hand the inductors are connected in parallel, then the equivalent inverse of the inductance would simply be the sum of the inverses of the individual inductances, much like the resistor. One of the main laws, now coming to circuit laws, one of the main circuit laws that we can use for analysis of our circuits is called Kirchhoff's voltage law, the KVL. And what the KVL simply says is that for a circuit, the sum of voltage differences around any closed loop in a circuit must be zero. So this is an example of a closed loop or a circuit. And then we see that you have a supply voltage and element number 1, voltage across element number 1, voltage across element number 2, voltage across element number 3, and so on and so forth, up until voltage across element number n minus 2, n minus 1, and voltage across element number n. Now what the KVL says is that the sum of the voltages around this closed loop circuit has to be 0. So what it simply means is that the positive voltage here, the supply voltage minus all of these other voltages, V1, V2, V3, V4, V5, V6, and so on and so forth up to Vn, has to be 0. So this is the first way of expressing the KVL. Or we can reorganize it to mean that the supply voltage will be equal to the sum of all the other voltages that are being supplied. So you can reorganize the same equation to put it in this format. But that's the KVL for you. The next circuit law, which is interesting, it's called the KCL, the Kirchhoff current law, which simply says the sum of currents flowing into a node or a junction must be equal to the sum of currents flowing out of it. So the amount of current is conserved. So if you have a junction and you have currents flowing in and other currents flowing out, so if you have current 1 flowing in, current 2 flowing in, current 3 flowing out, and 4 flowing out, it simply means the current in 1 plus the current in 2 have to be equal to the current in 3 plus the current in 4. Or we could say the current in 1, current in 2, which are positive because they're flowing in, minus the current in 3, minus the current in 4 because they're flowing out, has to be equal to 0. That's what the KCL simply says. So current flowing into a node must be equal to 0, or the current flowing into a node must be equal to the current flowing out of the node. So the node will not store any current. So here you have a good example of a current supply IS, where the current flows all into this node, and then from there I1 gets its own current, I2 gets its own current, I3 gets its own current, I4 gets its own current, and so on and so forth up to IN getting its own current. So what the law simply says is, we therefore can say the current flowing in IS must be equal, because the current into this node is IS, must be equal to I1 plus I2 plus I3 plus I4, I5, I6, and so on and so forth, up to IN. Alternatively, we can put the same law, we can put it this way, that IS minus I1 minus I2 minus I3, and so on and so forth, must be equal to 0. That's the current circuit law. So this gives us, the two circuit laws will relate the amounts of current totally within our systems, in order to give us the differential equation. So we can conveniently use either KCL or KVL in order to derive our models for electrical circuits. Now let's look at an example. So we have a circuit here, and then this circuit we need to derive a differential equation model for a circuit with a supply voltage UT, supplying the following elements, supplying an inductor L and a resistor R and a capacitor C. So we need to derive a differential equation model for this. So we can use, in this case, because we have a single loop, we can use KVL. Remember, KVL simply says that the supply voltage will simply be equal to the sum of the voltage drops off across each of the elements. So our supply voltage, which is U of t, will simply be equal to voltage across the inductor plus the voltage across the resistor plus the voltage across the capacitor. However, we have previously learned that the voltage across the inductor is proportional to the change in current. So V is equal to L di dt. Therefore, the voltage across the inductor can be simply represented as that. And we have also since learned that the voltage across the resistor is simply equal to the current multiplied by the resistance. And we have since known that the voltage across the capacitor, the voltage across the capacitor times C is simply equal to the integral of I dt. So therefore, we can substitute this equation into our KVL to give us 1 over C times the integration of I dt as the voltage across the capacitor. So now all of these voltages have to be equal to the supply voltage, which is U of t. So using KCL and these fundamental relationships of how the individual elements work, we are able to derive then a differential and integral equation here, because we have an integration here of our LRC circuit. Now, if you take an example a bit further, can we then create a transfer function model of a circuit where the input is U of t and the output is the current flow in the circuit? Now, beginning from our KVL, we know that we have established that this relationship holds in this circuit, that U of t is equal to L di dt plus R times I plus 1 over C, the integral of I dt. So we have previously considered in the previous lecture and in the previous course that you've learned control systems 2, that the we can transform this into a Laplace transform. This equation can be transformed using Laplace transform, and using zero initial conditions, we know that we simply replace the derivative with multiplication by an s, and we replace the integral with division by an s. So we can therefore take this equation to this form, where u of s is equal to L. Because we have di dt, we replace that with multiplication by an s, and then we come to plus the resistance times I of s plus 1 over c times the integral of I. But because we have the integral, we know that we can replace it by 1 over s times I. Now, having done that, we come to this equation. Now we first multiply by sc throughout, and then that gives us that. So we have sc times u by s, and then we have s squared times lc I of s, and then we have s times rc I of s, and then the sc is removed from the bottom here. And then we can therefore, on the right hand side, collect the, we can factorize by I of s, and then we get this, the common factor here, we have s squared lc plus s rc plus 1. Now this is equal to sc over u of s. And so we can calculate the transfer function, which is simply the ratio of the output over the input, and this gives us the following transfer function, that sc divided by s squared lc plus s rc plus 1. So this is what the transfer function of the LRC circuit becomes. So we can definitely, depending on the situation, adopt either KVL or KCL, whichever is appropriate, and use the fundamental relationships of current and voltage for each of these passive circuits L, R, and C. So far we have established how to then analyze RLC circuit and to create models of RLC circuits. So go on to the tutorial and tackle some of the problems that relate to the analysis of RLC circuit models. And you can also use the prescribed book at the relevant chapter to go and practice your skill on creating models for RLC circuits.